Hey everyone, today we have Dr. Garth Highland, and Garth, welcome to the 𝘺😰 podcast show.
Thanks. Glad you could have me here.
Yeah, it's a pleasure to have you here. I guess we met. You were Chad Polk's roommate at one point, right?
Yeah, that's right.
I love it. That's awesome. So yeah, so for folks that don't know you, Garth, if you can share your journey so far.
Sure. My name is Garth Highland. I went to grad school at K-State for statistics, which is kind of how I made some friends in the swine nutrition industry through Chad, yourself, and Jeremiah. So from there, after graduating, I wound up in Nebraska, working in a feedlot environment, and I was hired there to be involved with design experiments mostly, but wound up working on sorting algorithms for cattle, which was a very interesting field to be in at the time. So there was a lot of like designing experiments towards that goal. It was a very rewarding thing to be working on, and a lot of developments were made there. Since then, I've been working in healthcare. I currently work in the architecture environment, helping solve architectural problems and engineering ones. So I've had my career thus far has had an interesting arc. This animal agriculture has always been a part of it for me. So, which brings me to you. I'm happy to be here.
That's awesome. And would you say your experience would be both in designed experiments, but also on big data, right?
Yeah, both. So in grad school, I really gravitated towards designed experiments and enjoyed that. But then as soon as you get into a production environment, you're also looking at lots of data. So there's the design experiment side and what I'll call observed data, where you're looking at historical data, trying to pull out trends, make sense of it for your users.
Right. And can you comment, for those that are not familiar, on the difference between the two? I've mentioned this before on the podcast here, sometimes sitting with friends, watching some Netflix documentary, and especially, when it gets into human nutrition type of thing. And I have one saying that it's today you can prove anything that you want. You can find one paper that is showing anything. Mm-hmm. But then how do you work into like, okay, some stuff we need to use observational data, right? And then all the way up to getting closer to a cause and effect. So I know it's a long question there.
Yeah, a lot to unpack there. I would say that observational data is a great place to maybe hunt for a hypothesis, might be one way to think of it. So you're maybe testing out an idea on what's A versus B looking like in production. But then when you moved into so you're looking for correlations, right? When you move to the design experiment world, then you're testing cause and effect. Like it's not just correlation, you're looking for a causal treatment effect, which is proof. Then that's your real evidence.
Very cool. And the core of that, because everyone here, right, association is not causation, and then let's make it simple, right? So, okay, how do you make that transition? And I guess, is that a fair way to say that it's randomization is one of the core of principles of that, but is there other things?
So a good, well-designed experiment, randomization, understanding your treatment effects, and you might hear a statistician talk about scope of inference to understand, like, are you testing the population that you're wanting to infer upon? And then there's the thing, Simpson's paradox, which might be, that's kind of a whole other topic, but that is found when it happens all the time. You're in a production environment, you go to your database and you want to answer this question, you pull out A versus B and say this mean is higher than the other, therefore we're going to make this production decision. But you have excluded all the other variables that are going on, which may actually reverse what you're what you're trying to say. So I feel like I've kind of wandered a little bit away from your question, but when you design an experiment, you get to control for all the other things that may cloud your decision-making ability.
Super cool. So can you dive a little bit on the Simpson paradox? I'm not familiar with that, so I think I understood the overall, but can you give maybe a little more practical example?
So I'll just make one up. And briefly, Simpson's paradox is when you have some data and you found a trend using regression, and it's a positive trend, let's say. But then when you add another variable, let's say you have 2 years worth of data, you might find that the trend line is actually the opposite way, but the 2 years of data are far enough apart that it incorrectly causes you to see correlation in an opposite direction.
Okay, right. So just looking maybe, hey, I'm just looking at one flow of animals, or like 1 year, like you said, now you're looking at 2 or 3 years in that. Okay.
It's how two people can come to a meeting after pulling data from a similar source and disagree on something. It's because there's other variables at play. Maybe we've excluded something here and not over here. That's what's going on.
Super interesting. You also mentioned right, let's call it the scope of inference. Is that what you call it?
Scope of inference, like what you're looking at. Yeah.
Right. So we've seen very often folks, hey, let's eliminate this light pig, not eliminate, but eliminate from the study these light pigs, these heavy pigs, this thin sow, this heavy sow. Let's just use, I even heard the word before, the filet mignon, right? These optimal animals. But then, can you just explain the problem with that?
That's a great segue for some stuff I wanted to talk about with you. So we'll just start there. Designed experiments. This happens all the time. You set it up, you allocate animals, and then either at the beginning of the trial, during the trial, maybe an animal is sick. We don't like an animal for whatever reason, we remove it. Or in the data post the experiment, maybe we'll look at Cook's distance, like an influence diagnostic, and say, what's going on with this animal? Because it's influencing our inference, right? So we don't exclude it just for that reason, but we say, hey, researcher, what's going on with that animal? Oh, it was sick, gone, it's gone. So we're removing those the animals that are on the tail of the observation, right? That's fine. There's no real problem with that, because when we design an experiment, we're testing A versus B or whatever our hypothesis is, and we're interested in that treatment difference. So that's fine. The issue is when, and of course we've done our residual diagnostics. Everything looks nice, normally distributed. Everything's good. It checks out. We find a treatment difference. We implement that into production. Great. Everybody wins. But the problem is when we then start to take like the mean and standard deviation point estimates from something like that and applying it to a huge population of animals, that's where we start to run into problems. Let me back up for a second. So let's talk about average daily gain. This is a place that I've seen this phenomenon before, so we can talk about that intelligently. Let's say average daily gain on a per animal basis. Let's say there's some theoretical upper limit to performance that exists, just a hard stop. But then if you look at all the gains of all the animals, you're going to have animals that don't gain at all. Some extreme case, animals that die, animals that gain very poorly. So that distribution actually is bounded by some theoretical maximum. There's your average, and then you have this long tail of possibilities on the left side. So now if you're applying a symmetrical idea to a large population of animals, you are basically going to overstate performance. because you might want to just, when you're reporting, maybe exclude these poor performers, but you own, if you're in production, you own that animal too, right?
Right.
So we have this left tail, and we need to account for that if we're managing large populations of animals. So this is an argument that we're applying symmetrical ideas to a large population of animals that does not perform symmetrically. So when you start to calculate, for example, risk around heavy carcasses is something that I've dealt a lot with. You are going to not be able to project that accurately if you aren't considering all the possibilities of gain for animals.
Very cool. So from a more practical standpoint, how do you analyze that, right? So now you wouldn't analyze as a normally distributed, right? Or how would you go about that?
So I use a simulation framework to deal with that. So I don't need to describe the distribution in average daily gain on an animal basis. I just need to have observed it before. So if you have weights, experimental data where you have weights going in and out, or production data, ideally, where you have weights in and out and time, and you can get to average daily gain on a per animal basis. And can you build a histogram of average daily gain of individual animals? That's your distribution. And you leave all those poor performers in there. They're rare, but they're there. So then you can sample from that distribution then in order to make your projections. Very
interesting. And you definitely you exploded my mind here. So let's put a few comments here. One is that we're talking very large data sets, right?
Yeah. So this is something that becomes more pronounced as you look at larger and larger groups of animals.
Okay. Just so those folks that are listening to us, and most of them would be doing smaller designed experiments, or even what we call large scale, which is 1,000 cells, but it's still design experiment. You are going more on the big data type of scenario, almost, right? Is that
production? Like I'm not trying to pick apart how we design experiments, because that's not the goal. Right. It's this is production dollars and cents. View.
Yeah. Amazing. Yeah, just want to make that comment. And then let's see. So then, is there a name for this simulation, just so folks can reference?
I just call it a simulation framework. It's more of an idea. You run into it in Bayesian. Like some of this is going to be borrowed from Bayesian. So there's a small plug for why we should all be Bayesian statisticians. But it's more of a sampling methodology than we're most accustomed with.
Okay, and we definitely to dive into the Bayesian and frequentists, right? So if I'm using this correctly, for the folks that are not familiar, the whole thing around p-values and the holy grail of p-value 0.05, which is different from 0.06, but not 0.04. We should
arbitrary, right?
Yeah, arbitrary. And so if you can just explain to folks, the frequentist versus the Bayesian, and like you said, why we should go to Bayesian, and also maybe we can touch on how to do that. It's a massive change. I mean, you have editors that are doing this for 30 years. It's gonna take a few decades, is my guess, in our industry, but we can dive that area as well.
So I'll be brief on this topic, but I would say one highlight would be that, and this applies to what we're talking about here in using a simulation, is that your output is then a range of possible outcomes. And so, and then you summarize that information. So then you make specific probability statements around, like instead of 0.05, you can say, what's the probability of this difference? And is that a meaningful economic difference? Or if you know what a meaningful economic difference is, then you look for the probability statement around that difference as opposed to saying 0.05 winner loser. Let's get back to carcasses. So if you have an upper limit in which you receive discounts for carcass weight, in using simulation, you have a probability of risk around going over that. So you can say, what's the percentage of our animals that are going to be over this? Does that fit our risk profile for as a business? So it's all kind of the same. It intuitively matches the way we think about things. And a lot of frequentist math comes out of a time when we didn't have high-powered computers, but now we all have one of those. And so we can get back to using our computing power to make better inference.
That's super cool. I mean, and can you dive a little bit? I've heard the term a priori on the Bayesian side. Can you explain a little bit of what that means?
So we're really reaching deep into my schooling here. A priori is when you have a prior belief around a parameter that you're wanting to test. So if you have worked in a field and you're testing a hypothesis and you maybe think you have an idea of what the treatment difference might be or the ballpark, that's your a priori, that's your prior belief in something. And then that is in a way your starting point. And then you add data to that information and see how it changes.
Okay. And would that add more bias or no? Because that's just an arbitrary start, but you are going to back it up with data.
Your goal is to essentially overwhelm that prior belief or confirm it. And so is it changing? Or so you think of distribution around your belief of a parameter, like it's wide, is it confirming it, making a narrow distribution, or is it changing it at the same time? Is essentially what we're talking about here.
Very cool. And now back to the frequentist and the 0.04, 0.06, right? I mean, you as a statistician, the magnitude of difference, if you will, between 0.04 and 0.06 is the same one for like 0.20 and 0.22, which is 0.02, meaning this whole thing that we created to make it simpler, but it's still a continuum, I guess. That's my question.
So we're really talking about the probability of being wrong. Like we're talking about an acceptable probability of incorrectly declaring a treatment difference. And at some point that was set to 0.05 and we didn't look back.
Yeah, exactly right. Yeah. And it's crazy, man. That really dictates the whole science world right now.
Right.
With the exception of the areas that use Bayesian. Is there an industry that like majority what they do is Bayesian right now?
I believe that in like epidemiology, there tends to be a lot of Bayesian things going on. And I think in like computer science, you start getting into like getting towards your AI type of neural network stuff. There's some Bayesian things going on in there, but even in animal science, there's Bayesian statisticians. And oftentimes there's largely agreement between frequentists and Bayesians when it comes to outcomes. So sometimes there's a middle ground of, is the juice worth the squeeze of going to a Bayesian framework if we think it's just going to agree with frequentists. But like if you look at the interpretation of a confidence interval, that alone, like saying that 95% probability that the population parameter is in between these two numbers is intuitive. And oftentimes when you're given a frequentist hypothesis or confidence interval, that's the interpretation we all have in our mind. So why not provide that in the first place?
Right. And I was going to ask you, because I saw a paper a few months ago now mentioning, hey, we should move to confidence intervals instead of just the p-value. What's your take there? Would that already be a step forward? For example, we talk about, in our world of nutrition, we talk about, hey, the requirement was 18% of tryptophan to lysine, and maybe we should be looking, hey, 95% confident, that is between 16 and 20, whatever. That's one example.
I could see that being very useful for somebody in production. Like you're in a production environment, things are happening, and helping that person understand, like, maybe I need to be in this range or around here is really the value, like, as opposed to I have to absolutely perfect or it doesn't work for, I'm trying to apply it to the usefulness of science as well. But I would agree, like, confidence intervals are very important.
Very cool. Very cool. Well, let's see what else we have here. How about power analysis, Garth? I mean, any insights there?
Yeah, so that kind of ties into the simulation framework and what we were talking about with, making projections for populations of animals using a non-symmetric look. We're sampling from distributions. So if we're comfortable with simulation and what it means, we're sampling, we're doing things like thousands and thousands of times. Now let's go back all the way back to the beginning with our designed experiment. We're designing an experiment. We have data from past experiments, so we know what type of errors we're going to see in different parts of the experiment. So if we design an experiment, we should be able to analyze it before we do it. Now it's interesting. So we can say, and we know the treatment difference that matters to us. That's also is the key. So instead of going to the back of our old textbook to coming up with how many blocks we need or how many experimental units we need, we can design that experiment in our software and run it 1,000,000 times, sampling from our past data and building in a range of different treatment differences to understand what's our expected power, how many blocks do we need in order to prove what we're setting out to do. And that'll point us to, is our experiment too complex? Maybe we like power because we're testing too many things at the same time. All these things you can answer before you do an experiment, which is where the real cost is. And you can analyze it beforehand. You already have your software set up.
Wow. So that's basically taking, well, not everyone does a power analysis. They probably should, but the ones that do probably at one point in time type of analysis. And what you are saying, we probably should be doing a simulation out of that. Is that a fair statement?
Well, so this isn't a one size fits all thing. Like, I know that a lot of people do very similar experiments over and over again, testing for different things. And if you know where you're at and you've done that in the past, like, maybe that's not what we're talking about. But if you're really going out into the unknown, you're thinking about doing a different type of experiment, you should consider testing that out analytically before you get real experimental units involved. And it's an upfront cost, but it could prevent a downside after you do your experiment and then you realize there's no treatment difference. You could be just not having enough power, and that would be a missed opportunity. And I've encountered experiments where you're wanting to test equivalency and you're looking at mortality of two drugs, that is a very difficult thing to prove, right?
Wow, that's a great point, right? Especially on the, and correct me if I'm wrong, but on the frequent test, it's not designed to prove that two things are
the same.
The same, right?
Right.
So that's that we see that once in a while in nutrition as well.
Mm-hmm. And that I've seen it coming from like a sales perspective. Say, we'll provide you this drug, test it against what you're using, and if there's no difference, like, why are you using that drug if mine's $1 cheaper? Well, we probably don't have enough power for that experiment.
Right. And one way that we've found to be helpful is, but then now you probably need either a design experiment or a well done large scale type of perspective analysis. But you would have your control, regular or positive control, and then you'd have a negative control where you really penalize the performance. And now this drug or whatever product need to bring that negative up. Is that really like the fire test there? So basically, what I was trying to say, you would have your control, right, in a designed experiment, and then you'd have a negative control, let's say, that's going to reduce performance by 10%. Okay. Now you have a third treatment, which is that negative control with your solution. Could be a drug, could be an additive, whatever it is. And now, because the frequent test is set up to show differences where they are, instead of, like you said, not show something is the same. Now you are bringing that negative control up. So you're trying to improve that. Now you say, okay, yeah, there's something there versus, right? Is that a fair statement?
Yeah. So the test against the negative control is going to be maybe easier to prove than your treatment A, for example.
What's been, as you interact with animal scientists and veterinarians, what's been the one thing you're like, wow, I wish these people knew about this, or a common a common mistake that you've noticed?
So I kind of feel like I came in here guns blazing with some stuff that I've seen and in the past. This industry has a component of legacy to it, I've found. So like there is you might encounter somebody who's of the mindset that this is the way my father and grandfather did it, for example, and that's how we're going to do it. That's overcoming that, let's call it confirmation bias, is being able to overcome that is a good skill set to have in this industry, in any industry really, but that's something I've encountered.
I love it. It is more related to, you'd think that just in general, or maybe more related to analysis, or no?
Maybe in general. And not all producers have a statistician on board. Maybe they consult with one, or maybe they have somebody like you on that can handle the stat side of the design experiment within the context of, the swine nutrition industry. But I guess what I'm trying to say is that I might be a fresh perspective. For example, going into a new industry, which is something I have done a lot of, I'm kind of afforded the opportunity to ask stupid questions and challenge some of that framework of why do we think that way? Why are we seeing that from that perspective? And that can shed light on our biases and maybe where we need to challenge ourselves.
Very interesting. Do you see, in your experience as well, do you see, or do you have any recommendations for our industry or nutritionists or veterinarians to better work with statistician? When I say better work, it's probably better use statisticians?
So before there's data is a good time to talk to us.
Yeah, before you collect the data.
Bringing somebody on board to look at historical data, that is what it is. But if, you know, back to design experiments, if we're looking to do something new, it's unknown, that might be a good time to say, this is what we're thinking in terms of an experiment. How would that work? What does that mean for, what does block-by treatment interaction mean? Can we test for that? All these things. That's a good time to have a statistician on board to just talk through those ideas.
Very good. Well, anything else here before we wrap up the stats session, go into the 3 questions, Garth, that we asked every guest? Any final comments? No,
I think like this has been a really good conversation. So if you have anything else for me, I'm happy to hash it out.
Appreciate that, and it's a joy. I guess I had one question, which was, what's the difference? Is there a difference between a statistician and a data scientist?
Okay, so historically, like a statistician goes to school, there's a framework for what you're learning, and you get a diploma, and you're a statistician. You got your, you know, but historically, data scientist is has been a self-applied thing. Like you can be an economist, statistician, you can be a finance person, and because you're looking at, or a computer scientist, and because you're looking at data, you can call yourself a data scientist. Now it's a little more, that's changing now. Like there are data science curriculums that are popping up, so it's becoming more defined in terms of like you have to know some stats, you have to know some math stuff, you're engaging in machine learning type of things as well. And so there's kind of the umbrella of what a data scientist is becoming more defined.
Very cool. Have you ever dabbled into machine learning a little bit, or not quite?
Technically, yeah. So some of the big simulation work I've done in the past, instead of looking at carcass characteristics, for example, and sampling from past data as opposed to building a logistic regression model that spits out an output, I might just go sample data. And so that's like a nearest neighbors regression technique. Technically, that's machine learning. And the farther I go in my career, the more I am looking for techniques like that. But
that's cool. So for folks, and I asked that because I found that in my basic understanding is that machine learning is not too far away in a simple way from a regression, multiple regressions. Is that fair, or that's too out there?
Machine learning is it's kind of a bucket that holds a lot of things, and so there may be techniques that are similar to what you're describing there, but it can be tricky, and it gets back to part of the role of the statistician or the data scientist is to understand the context of what they're doing, such that, back to scope of inference, such that we're saying the right thing about the right population, as opposed to going over here, running something that I don't understand, and then applying it carte blanche to a population. That's the risk of like your canned machine learning things that are kind of coming out.
Very cool. Awesome, Garth. So let's get into the 3 questions we ask every guest. The first one is, normally we ask the pig-related book, but you might have one, but you might have a livestock, or you might just have a stats-related book that you prefer the most.
Oh man, that's a tricky one. I wish I just moved, so I don't have all my cool books handy. There were some that we used in Stats 704 and 5 that was all about linear regression. And I both took that class, and then the next semester was like the teaching assistant for that, for some of your peers, actually. Yeah. That is like the backbone of a lot of what I do.
Was that a messy data class or not?
That's another great class, is messy data, when you're understanding heterogeneous error variance is invaluable in design experiment environment. So there's 2 books. Super
cool. How about a book outside of agriculture or outside of stats as well, just in general? Can be, we have had novels, it could be anything.
So you're gonna laugh, but a lot of the books I read tend to be of like the repair manual variety, or stuff about woodworking, which is a hobby of mine. So I'm very hands-on outside of work. So I'm looking at like books about horticulture, books about fixing stuff, or woodworking, or like cookbook type of stuff.
That's cool. That's cool. I love it. I love it. All right. And the final one is what sets apart successful professionals than those that are not, in your opinion?
I've found that communication is what sets people apart. Being willing to and able to clearly communicate, and then also listen, because it's not just me conveying my idea, it's also listening to yours and allowing that to inform the way I think as well. I find that to be a open person that I've seen succeed.
I love it. Yeah, it's a tough one, right? I've been trying to get better on that over the years, and I mean, I think humans in general, right? Your default almost is like you're listening to someone, but you're already thinking what you're gonna say next, which is terrible, right? And if you're gonna have a meaningful conversation, you really need to stop and listen, and then it flows.
Right. And I think that that's harder maybe the older we get, because our experiences confirmed in our, it confirms our beliefs, but remaining open to influence is a valuable skill.
Awesome. It's been a joy, Garth, to have you here. I think you're officially the first statistician and a data scientist to be here with us, so I appreciate that.
That's great. Thanks for having me.